Hello, I'm Giovanni. At Eurocom, we are developing an open source RAG system called Euler for research and education. During our project, we realized that we needed a way to validate our system. We are most interested in improving the factual correctness of answers. We found several ways to do so, but little on whether they work or not.
So, the big question. We need to validate LLM outputs, but can we trust the judges? Let's say you want to build an AI assistant. But how do you know it works? One simple way is to query the system and manually check if the outputs correspond to what you'd expect. But then you would figure out that this is tedious and time consuming. You would need to do this extensive testing every time you deliver a new version of your model, or when changing your LLM pipeline. So you need to create a set of questions and expected answers. But how do you know the LLM output is good? Well, you could compare the expected answer and the LLM generated answer. In fact, there are several ways to do it. Historically, you could use the rouge or blue scores that use n-grams. This is a bit unreliable because it does not capture semantics. Or you could use the semantic similarity scores as BERT score. However, semantic similarity does not guarantee truthiness. For instance, if you ask the question, what's the color of the sky? And the ground truth says the sky is blue, while the LLM generated answer says the sky is orange, you would observe a strong semantic similarity because they both are talking about the color of the sky. Another way is to use natural language inference-based methods such as FactCC. These methods have a better interpretability, high alignment with human ratings, but they face challenges with fine-grained fact-checking. A modern trend is to use LLMs to evaluate the output of LLMs. The Prometheus model is one of a kind for the LLM as a judge models. The biggest advantage of such methods is that they are very flexible and surprisingly, they've been reported to correlate well with human judgment. However, there is always the recursion problem. Can we trust an LLM to check another LLM? And the last option are metrics that chain LLM operations to extract and compare facts between the system output and the ground truth answer. RAGAS factual correctness metrics is one example of this class of methods. But which method works and which don't? How can we know this in a systematic way that is beyond anecdotal cases? We decide to put that to a test. The general idea is that we seek to simulate the output of the AI system to various degrees of error. Then, we can check whether the assessment methods correlate to the introduced errors. Let's see it more clearly with an example. In this example, the user asks, who did the United States win its independence from? The long answer for this question includes several details on the adoption of the Declaration of Independence on July 4, 1776, and that the Continental Congress declared the US as a new nation separate from Britain. We could, for example, decrease the factual correctness of the answer by changing the dates which the US became an independent nation. Then, we could go a bit further and modify other terms, such as saying that the adoption was a proposal and who it gained independence from. And then we could make it slightly worse by saying that the Declaration of Independence was a treaty. And closing by saying that US is not really a new nation, but rather a more generic term such as a unified region. As one can see, we can build a set of answers to the question with an increasing level of controlled wrongness, while keeping the answer semantically plausible. If we had a dataset with such set of questions and answers with varying degrees of errors, we could put any evaluation metric to assess Q&A pairs. And we can check whether the assessment methods capture or not the introduced errors. That's the main idea of our project, building a tool for systematic assessment of evaluation methods. But how can we build such a dataset? First, one could ask a group of people to write it by hand. That's a bit of work. It takes finding the important points in the answer and modifying them smartly, so to keep it plausible. Probably one would run out of energy before doing so for a large dataset. Or Option number 2 is to use AI. That reduces the amount of work for certain. But is it trustworthy? The answer is that under certain conditions, yes, it can work. And this is how we did so. We selected a topic and created a gold dataset. This gold dataset has several questions and ground truth answers written by experts on the topic of their choice. Then we asked another group to create a dataset with varying levels of wrongness in answers while following a set of guidelines. The answers must be wrong in a uniform and in a way that's still plausible. Then we designed a pipeline that combines natural language tools, LLMs, and plain old programming to try to do the same. From what we observed, neither our pipeline or experts are perfect on this task, and some of what they will produce may have arguable quality. As perfection may not be a feasible aim, we prefer to test if our pipeline performs at least as well as experts. If that's statistically true, you can run our pipeline and trust its output. Sometimes it might not work that great, but humans wouldn't be perfect either. So if the pipeline works better in average, that's a win already. It means less editing effort if you truly need a perfect dataset. To make such a validation, we asked participants to compare, according to certain guidelines, the dataset corrupted by humans versus the same dataset corrupted by our pipeline. To facilitate comparison, we crafted an ergonomic UI where evaluators can visualize the differences between each response level to the previous one. They can also choose between the answer on the left, right, accept, or reject both. The AI and human perturbations are randomly positioned, and the evaluators are blind to who is who so to minimize bias. We assessed 20 questions by 5 perturbation levels, which totals to 100 Q&A pairs. We asked 2 validators to rate each pair. In this chart, you can see the distribution of choices between experts. Roughly, you can see some level of agreement between them, or more precisely, a coherence kappa of 0.1. Generally, we experienced that even if our guidelines are comprehensive, the assessments take some level of subjectiveness. We also looked at the general quality of outputs between the noise and generation levels. The first level, which consists of simple paraphrasing, got a near-perfect equivalence between our pipeline and expert-generated outputs. For the other levels, we observed around 80% resultant ties, that is, evaluators choosing both are good, meaning practical equivalence. Regarding the remaining data, we observed that statistically, the pipeline got a slightly better performance than humans on this task. Post hoc analysis estimates 77% power for non-inferiority of the pipeline at a confidence level of 95%. Well, but what does the pipeline looks like? Building the perturbated answers takes a series of steps which may or may not involve LLMs. Starting from a gold dataset of Q&A, the first step uses an LLM to paraphrase the ground truth answer. The LLM is instructed to preserve all the details of the original answer. The second step uses a syntactic and dependence parser to identify most significant factual components of the answer, such as entities, quantities, and modifiers. The elements are tagged within the text. Then, the pipeline selects each component and eliminates the terms that appear on the question itself. The goal of these steps is to avoid catastrophic modification. For example, if the question is, what's the color of the sky? And the answer is the color of the sky is blue, the goal is to avoid changing the answer to the color of the sea is blue, which it wouldn't make much sense in the question's context. Then the pipeline uses an LLM to rank items by order of importance to the question. So to emphasize main events, actors, implications, or numerical details, while de-emphasizing vague or ancillary terms. The pipeline filters elements of low value and build groups of factual elements while trying to balance low importance components to ensure that each perturbation level increases progressively. Starting from A0, the paraphrased answer, the pipeline incrementally selects grouped factual elements and requests an LLM to modify the factual items in a plausible but subtly incorrect way. Now, let's get to the most important information. What algorithms work best? To answer this question, we select 100 Q&A from the 300,000 Google Natural Question dataset and used our pipeline to generate 500 examples of perturbated answers. We kept the first 100 Q&A with answers more than with 250 characters, but not longer than 700 characters. We did so because we want to test assessment's algorithm's ability to detect errors on comprehensive questions we typically see in modern chatbots. We compared 3 candidate algorithms: LLM as a judge, which is a popular technique that uses an LLM and prompt engineering, RAGAS, factual correctness metric, and a variant we developed that uses open weight models and natural language inference. We call this later metric TruthScore, which has also been open sourced as part of our project. We compared the algorithms on 2 metrics. The first is the Pearson correlation that measures a linear relationship between the algorithm's judgment of correctness against the perturbation levels. The second metric is the Kendall-Stahl that measures if the ranking of alternatives is preserved. In other words, it measures if the assessment algorithm consistently classifies perturbated answers in the expected ordering. The correlation values are negative because we are verifying a correctness score by the perturbation level. The higher the perturbation level, the lower should be the correctness score, thus negative correlation. The first thing that jumps to our eyes is that LLM as a judge consistently underperform pipeline-based methods. Among the pipeline-based methods, RAGAS using GPT-4o Mini got the best results regarding Pearson correlation. The Kendall-Stahl was slightly worse than our alternative, but the difference is not statistically significant. TruthScore is good and comparable to the best method. Using only open-weight models, TruthScore is a robust alternative if you want to avoid the cost of API calls to paying providers. We also looked at how the model size impacts the performance of LLMs regarding the factual correctness. We tested several LLM providers, model sizes, and task fine-tuned models. The blue dots represent the LLM as a judge, while the green dots are the pipeline-based methods. As you can see, pipeline-based methods are providing a better Pearson correlation, but the performance does not improve if the models get larger. We also tried smaller models than Gemma 12 billion. However, these models did not respect formatting constraints, such as producing JSON outputs reliably enough to provide an accurate picture. Regarding LLMs as a judge, we see a small but statistically significant improvement for modules exceeding 10 billion parameters. However, the improvement seems to stagnate quickly since the increase in the model size by a factor of 5 did not produce any visible gains. Let's close with our contributions. We defined a new benchmark for assessing the evaluation algorithms for factuality called TruthBench, which is open source. We are also making available an open weights factual correctness metric called TruthScore that you can use with the RAGAS library. And, well, happy LLM validation.